Hey there, Seahawks. It's Miss Adams, and in this video, we're going to learn about chi-squared tests. All right, so the types of tests. There are no intervals for chi-square. There's a goodness of fit, and then there are homogeneity and independence. They're a little bit different, but they kind of are together. A goodness of fit test is always going to have just like one row of data, and homogeneity and independence are going to be put in a two-way table. They all use the chi-squared variable for their test statistic, and they all have the same formula for calculating that test statistic, which is the summation of the observed count minus the expected count squared divided by the expected count. All right. So the chi-squared distribution with 5, 10, and 15 degrees of freedom, so you can see kind of what happens as the degrees of freedom increases. It becomes more and more normal. Chi-squared is always going to be a right-skewed distribution. You do have a table that you'll be given when you take your AP exam. So if you have the chi-squared value, you can find the p-value or vice versa using the table. And it becomes less right-skewed as the degrees of freedom increases. All right, so chi-squared test for goodness of fit is used to test whether an observed distribution fits or matches an expected distribution. All right, so state our observed distribution of, your context goes here, fits the expected distribution of context. The alternative would be the observed distribution of your context doesn't fit the expected distribution. All right. So you're going to write these out in sentence form. Plan, we have to be working with categorical data. You don't actually have to check that condition, but you want to make sure that you have categorical data there. Random, 10%, and then our large counts condition is going to be that all expected counts are greater than or equal to 5. If that's true, the conditions are met, we're going to be using a chi-squared distribution and be doing a chi-squared goodness of fit test. All right, make sure that you show all of your expected counts somewhere on your problem. All right, in the do, we're going to calculate the test statistic, write the formula, show the first two calculations or the first one and the last one, and then give the total. Then calculate your p-value. So if they give you your chi-squared value already, you have the chi-squared value and you just want to find the p-value, you could do a chi-squared CDF in your calculator under second vars in the distribution menu. Your degrees of freedom is calculated by taking your number of categories minus 1. All right. And then conclusion, it's basically the same two sentences. We reject or fail to reject the null hypothesis, and then we have sufficient or insufficient evidence to support the alternative. Make sure you put that all in context of the problem. All right, an example, testing to see if a die is loaded. What is the expected distribution of a fair die? So if a die is fair, we expect to roll a 1, 2, 3, 4, 5, and 6 equally, so 1 out of 6. I roll a die 120 times. What is the expected distribution in the number? So how many times would I expect to get a 1, a 2? So 1/6 of 120 is 20 each. I roll a die 120 times. Below is the actual distribution. So this is what was observed. Okay, so the middle table is my expected. The bottom table is my observed. All right, state the observed fits expected. So the observed distribution of dice rolls fits the expected distribution. My alternative would be the observed distribution of dice rolls does not fit the expected distribution. I am working with categorical data, even though they're numbers like each die roll. Okay, they could be colors on the side of the die. Random, we're going to assume that the sample is representative of the population. 120 is less than 1/10 of all dice rolls, and all expected counts are equal to 20, so 20 is greater than or equal to 5. So all expected counts are greater than or equal to 5. Conditions are met, and we're doing a chi-squared goodness of fit test. Our formula for chi-squared is the summation of observed minus expected squared divided by expected. I'm going to do the first piece and the last piece, so I'm doing observed minus expected squared divided by expected, and then the last one, I just put plus ... in the middle there. We get a chi-squared value of 8.7. Degrees of freedom is number of categories minus 1, so 5. My p-value is 0.1216. Okay, so I could do a chi-squared CDF, or I can put this all in my calculator. So I'd go to Stat Edit in List 1, I put all of my observed counts. In List 2, I put all of my expected counts. Then go to Stat Test, and we're doing a chi-squared goodness of fit tests. So you'll see a chi-squared GOF test. Observed is List 1, expected is List 2, and degrees of freedom is 5. All right, my picture, I'm going to draw a right skewed distribution. This is a chi-squared distribution with 5 degrees of freedom. 0 is going to go here. I'm going to go to my chi-squared value, 8.7. I'm shading above, and I had about 12% shaded, so looks good to me. Our conclusion would be we failed to reject the null hypothesis because our p-value of 0.1216 is greater than our alpha value. We have insufficient evidence that the die is unfair. All right, another example. Does the color impact the chance that a car is stolen? Suppose it is known that of all cars, 15% are white, 15% are blue, 35% are red, 30% are black, and 5% are other colors. A random sample of 830 stolen cars is taken, and their colors are noted below. Test to see if the cars stolen match the distribution of all cars. So state the observed distribution of colors of stolen cars matches the expected distribution. Our alternative would be that it does not match the expected distribution. Our alpha value is 0.05. You might want to throw the degrees of freedom in there. 2, number of categories minus 1, so 4. Random. A random sample of 830 stolen cars was stated. 10%, 830 is less than 1/10 of all stolen cars. All expected counts are greater than or equal to 5. All right, so for my expected counts, I'm going to do, I have 830, I have 15% that are white, so 0.15 times 830 is 124.5. 35 that are red, so 0.35 times 830 is 290.5. And so with my large counts condition, I'm going to list all of my expected counts there. All right, do the conditions were met. We're doing a chi-squared goodness of fit test. Here's our general formula. Here it is with the first color and the last color plugged in. Observed minus expected squared divided by expected. We get a chi-squared value of 66.33. Our degrees of freedom was 4. Our p-value is quite small, 1.35 times 10 to the negative 13th, which means it's 0, and then 12 zeros and a 1. Right. So basically 0. Draw our picture. We're going to have a skewed right distribution. This is a chi-square distribution with 4 degrees of freedom. Remember, the smaller degrees of freedom, the more skewed it is. We're going to 66, so there's not going to be a whole lot shaded, but it's okay. Conclude, because our p-value is quite small, so we reject the null hypothesis because our p-value is basically 0, is less than 0.05. We have sufficient evidence that the distribution of colors of stolen cars does not fit with the distribution of all cars. All right, so again, in your calculator, list 1, you're putting your observed values. List 2, you're putting your expected values. You can go to Stat, Test, chi-squared goodness of fit test, and then put your degrees of freedom in there, and it'll give you everything you need. All right, chi-squared test for homogeneity or independence. This uses two-way tables. It compares two variables that are measured from the same sample. Okay, so it's coming from the same sample. Two types of tests, homogeneity and independence. Gender versus college location. So we have male, female, in-state, and out-of-state. Homogeneity compares the distribution of several groups for the same categorical variable. So several groups but the same categorical variable. Is the distribution of grades the same throughout the years? Is the distribution of gender the same throughout the rank in the military? Are there differences in the distribution of type of car between student and staff? Is the distribution of political party different between genders? Okay, so the distribution is kind of a key word there. For independence, it examines the counts of a single group to test for an association between two categorical variables. All right, so some key words to look for are association, effect, independence, or relationship. Is there an association between grades and year? Does gender affect someone's rank in the military? Are type of car and type of driver independent? is there a relationship between political party and gender? All right. State, you're going to put your hypothesis, depends on which type of test. You're going to write your hypothesis to match the test. It's going to be in sentence form. Your null hypothesis will be that they're equal or no difference. There's a typo there. That they're independent or no association. Your alternative would be that they're not equal, or they are different, or they are dependent, or there is an association. Our conditions stay the same. The main new condition here is our large counts is that all expected counts are greater than or equal to 5. Do, we're doing the exact same test. To get the expected value, you're going to do your row total times your column total divided by your table total. So to get the expected value is a little bit more challenging. So gender versus college location, we have this. If I want to get my expected values, I need to first get the totals for the rows and the table. And so for male in state, I'm going to do the row total, 61, times the column total, 62, divided by the table total, 139, I get 27.2. I'm going to do that again for female in state, male out of state, and female out of state, sorry. All right, our p-value, we're going to calculate. Again, our calculator can do most of this for us. For this one, we're actually going to be using a matrix. We'll put all of your observed values in a matrix, in matrix A, and then you'll do the test, and it'll automatically make matrix B of all the expected counts for you, so you don't even have to calculate the expected counts for these ones. Your degrees of freedom is a little different. It's the number of rows minus 1 times the number of columns minus 1. All right, for the calculator part, you're going to put this all into matrix A, your observed values. So you're going to get second, and then x to the -1. You'll see the little matrix. And then you'll go over to edit, and you'll put in the dimensions. So it's row by column. And then you'll fill it in. You'll run a chi-squared test. It gives you a test statistic, a p-value, the degrees of freedom. And then you can go back and look at the expected values for matrix B. I like to look at it in the edit screen. I think that's the one where it makes it look a little bit easier to read. All right, a local college admissions officer wants to know if students' choices and majors have changed through the years. He selects a random sample of freshmen from 2005, 2010, 2015, and checks their choice of major. Test to see whether the majors are distributed the same each year. So that keyword distributed, and it's a two-way table. We're going to do a test, a homogeneity, chi-squared test of homogeneity. I'm going to calculate all my expected values. Okay. So again, to get all of these quickly, I'm going to put all of these into matrix A. So 1, 2, 3, 4, 5 by 3 matrix. And then I'm going to run a chi-squared test, and then I'm going to go back and look at matrix B, and I'll get all of my expected values. It is required that you list out all of your expected values. All right, state. The null hypothesis would be the majors are distributed the same each year. The alternative would be the majors are not distributed the same each year. Our alpha value is 0.05. My degrees of freedom is the row total minus 1, so I had 5, so it's going to be 4. I had 3 columns, so 2, because it's 3 minus 1. So I have a degrees of freedom of 8. Plan, I'm going to check. I am working with categorical data. It was a random sample. It was stated. The 10% condition, I could probably just add them all up, the whole table total, but I didn't. Okay, so I could do just the table total probably here instead of each individual. But there's more than that many freshmen, okay? Large counts, all expected counts have to be greater than or equal to 5. I'm going to just go ahead and say that the lowest one was the 2005 education, and that was 25.88, which is greater than 5. All right, our conditions were met. We're doing a chi-squared test of homogeneity. Again, I'm using that same formula, so I'm going to do the first one and the last one. And I get a chi-squared value of 30.22. I'm relying on my calculator here, so again, I put all my data, my observed counts into matrix A. Stat, test, chi-squared test. I get my chi-squared value. I get my p-value. which times 10 to the negative 4. Remember, p-values have to be a value between 0 and 1. They're probabilities. So if you see a number that's larger than 1, it's e negative something, means it's times 10 to the negative exponent. Draw my chi-squared distribution with 8 degrees of freedom. I'm going to go to my chi-squared value and shade above. And conclude. I'm going to say that we reject the null hypothesis because our p-value of 0.000193 is less than our alpha value of 0.05. We have sufficient evidence that the majors are not distributed the same each year. All right, our next example, example 4, smoking versus socioeconomic status. Below is a table of a random sample of 356 PA residents. Giving the smoking status versus socioeconomic status, test whether there is an association between the two variables. Does there appear to be a relationship between smoking and socioeconomic status? So I see both association and relationship, which are leading me to a chi-squared test for independence. So I need to find all my expected counts. Again, I'm going to put all of the observed counts into matrix A. I'm going to do a chi-squared test. I'm going to go back and look at matrix B. And here are all of my expected counts. State my null and alternative hypothesis. My null hypothesis would be there is no association between smoking and socioeconomic status. In other words, they are independent of each other. The alternative would be there is an association between smoking and socioeconomic status, or that they are dependent. My alpha value is 0.05, and my degrees of freedom is 4. So, number of rows minus 1 times number of columns minus 1. Plan, I'm going to check my conditions. Random was stated, 10%. There was 356 PA residents, so that's less than 1/10 of all PA residents. All expected counts are greater than or equal to 5. My lowest one was the middle and never, and that was 14.461, which is greater than 5. All right, so my conditions were met, and I'm doing a chi-square test for independence. My same formula, the summation of the observed minus expected squared divided by expected. I'm going to do the first one and the last one plugged in with numbers, and I'm going to get my chi-squared test statistic of 18.51. My p-value of 0.00098. I'm going to draw my chi-squared distribution with 4 degrees of freedom. I'm going to go to my test statistic and shade above. Our conclusion would be we reject the null hypothesis because our p-value of 0.00098 is less than our alpha value of 0.05. We have sufficient evidence that there is a relationship between smoking and socioeconomic status. All right. Go Seahawks!